As we talk more about the concept of random variables, I'll first introduce a specific type of random variables called discrete random variables. Now, a random variable is discrete if we can count the values that it takes. For example, the number of customers entering a store is discrete because it takes values 1, 2, 3, etc. Whereas the amount of rainfall on a given day is not a discrete random variable. It could take the values 1 centimeter, 2 centimeters, etc., but it could also be 0.45283 and any other value in a continuum. We'll leave those types of random variables aside for now. The math is a little more complex behind them, and we'll focus on discrete random variables for now. Here are a few more examples. The number of strikeouts before a hit in baseball is discrete because, again, you can count the outcomes. It takes the value 0, 1, 2, etc. The number of Red Sox supporters I reach if I call 20 phone numbers at random is discrete. And you can even do things like this. You can encode whether or not a person has a heart disease with 1 meaning yes and 0 meaning no. And then this becomes also a discrete random variable. Now, with random variables come the concept of probability distributions. And the nice thing about discrete random variables is that we can encapsulate these in something called a probability mass function. Here's an example. When I roll a dice, we are very familiar by now with the idea that each value has a probability of 1/6. And this is its probability mass function, expressed in two different ways. There's a table on the left and a graph on the right, and each of them show that the mass of the probabilities on the different values are distributed equally, 1/6 on each. Here's an example of a little bit more interesting probability mass function, again expressed in two different ways, in a table form and in a graph. This is the probability of the sum of two rolls, and you'll notice that the probability of rolling two rolls that sum up to 2 or 12 is very low, while the probability of rolling two rolls that sum up to 7 or even 6 or 8 are relatively high. This is shown in the numbers on the left and in the heights of the bars on the right. Now, in addition to being a visualization tool to help us see where the mass lies on the values of random variables, this is also an important computational tool. And to see that, I've replicated here some of the probabilities for the experiment of rolling 2 dice and looking at their sum. We're interested in the sum. This is the random variable. So let's see how we can use this for computation. Say, for example, you wanted the probability that the random variable lied within some range. Let's say 2 less than or equal to x less than or equal to 4, where x here represents the sum of the random variables. If I have the probability mass function, then I can calculate this. It's just equal to the sum of each of the probabilities for each of the outcomes of interest. So this is equal to 1 over 36 if x is 2, plus 2, over 36, or 3 over 36, corresponding to x equaling 2, 3, and 4. So this is a total of 6 out of 36, or 1/6. So probability mass functions are powerful, and we'll see that they can also be used to calculate what's called expectations, which we'll look at next.